All right, this is a short presentation on one of our learning targets that's a supplemental learning target, and it's about understanding the formal definition of the limit. I've created a little slide deck here, and I think I can write on it and annotate it as I go. In this class, we've learned to interpret these symbols here that's on the screen as meaning as x values get closer to c, the values of f of x get closer to L. In the 19th century, mathematicians agreed that this definition was imprecise. It captures what we mean by a limit, but it wasn't precise enough for the work that they were trying to do at the time. The questions they asked were, what does, quote, move close mean specifically, and how are the closeness of the dependent and independent variables related? These are questions that the formal definition of limit address. Mathematicians chose to measure the distance on the number line using the absolute value function. So specifically, that means that if a and b are real numbers, then the absolute value of a minus b is the distance between them on the number line. So think about the numbers 1 and 2. The absolute value of 1 minus 2 is 1. That's the distance between those two numbers. And it doesn't matter what order you do the numbers in. The absolute value of 1 minus 2 is the absolute value of 2 minus 1, and they both equal 1. So the absolute value is going to be giving us a way to talk about the distance between things. And in the case of limits, the distance between the input x and the input number c on the input number line is absolute value of x minus c, and the distance between f of x and L on the output number line is absolute value of f of x minus L. Right? So we'll see those two absolute value expressions appearing in the formal definition of limit, which is what we're going to see right now. So here's the formal definition of this limit statement. Now remember, our informal understanding of this is as x gets close to c, the values of f of x get close to L. Here's what the 19th century mathematicians did to formalize that. And I'll read it. We say the limit as x goes to c of f of x equals L if, given any epsilon greater than 0, there is a delta greater than 0 with the property that if 0 is less than the absolute value of x minus c is less than delta, then the absolute value of f of x minus L is less than epsilon. Here, the Greek letters epsilon and delta are representing a distance. This definition means that no matter how close, that is epsilon, someone wants the output value f of x and L to be to one another, we can find a small distance, a small interval around C that has the property that if x is in that interval and is different from C, then f of x will be closer than epsilon to L. So you might want to stop and read this paragraph again and look at the definition and maybe do that once or twice just to see how we can interpret the definition. And we'll tease this apart some more. All right. In practice, we have no control over the value of epsilon. In this definition, the way it's written, we don't have any control over it. It's given to us. Then we must find a delta that works for that epsilon. In a math class we teach in the math major, advanced calculus, students learn how to do this process for a wide variety of functions. They also learn the consequences of this definition and how it applies to other concepts. Now, that level of work is beyond the scope of this course. If you want to be a math minor or a major, you can take advanced calculus and learn how to do that. But for us, we want to be able to exercise this definition using graphical examples. So we're going to keep it simple. So here's an example. Consider the function f of x equals 5 minus 3x pictured below. According to its graph, the limit as x goes to 0 of f of x is 5. So I'm going to make sure this is right. The limit as x goes to 0 of f of x is 5. Suppose epsilon is 2. Somebody gives us epsilon equals 2. Find the largest delta greater than 0 that will work to guarantee that if the distance between x and 0 is less than delta, then the distance between f of x and 5 is less than epsilon. So this is how we're going to approach this problem. Okay, we focus on the epsilon equal to 2. That's our goal. Well, our goal is to find a delta that if we take x's that are within delta of 0, then we're going to be guaranteed that the function values are within epsilon of 5. So our epsilon is 2. What do we do? So here's a picture where I've got the limit value 5 here drawn in this horizontal line, and it's hard to see, but there's another horizontal value here that goes along with the 0 for the input, or where we're headed for the inputs. The next thing I'm going to do is I'm going to look at 5, and I'm going to go up 2 to 7, and I'm going to go down 2 to 3. Right? So in the end, I want my function values to be within 2, epsilon is 2, of 5. So that means I want my y values to fall within this interval on the output axis. So I'm going to come over here, look at this upper limit, and I see where it intersects my function. I'm going to look at this lower limit, and I see where it intersects my function. And now I'm going to draw lines down onto my input axis. So here I've got green dotted lines. These lines have the property that if you pick an x within the interval that's bounded by these lines, pick an x, it goes up as an input, and then we can go over here as an output, and we can see the output is within that interval that we wanted to stay within. So these green lines give us the limits of an interval, well, the extent, the endpoints of an interval, that if we take something inside that interval, it maps to our output interval that we're interested in. Now we want to find a single delta that gives us the distance from 0 in this case. How far out can we go in our interval? How far out can we go in our interval? In this example, you'll notice that this half width here and this half width look about the same. Looking at the tick marks on the x-axis, this x value here where the vertical green dotted line is, that looks like it's at about 0.65. And this here looks like it's at about negative 0.65. So the distance between 0 and the right endpoint is 0.65, and the distance between 0 and the left endpoint is 0.65. So this suggests to us that our delta can be taken as 0.65, because any x within 0.65 of 0, 0.65 this way or 0.65 that way, any x in this interval maps up and into this interval here centered at 5 that has a half width of 2. And that's how we do these functions, or that's how we do these problems. That's how we exercise the property or the formal definition of limit using the graph of a function. And that's what you need to know, or that's one of the things that you need to know for the Living Target quiz on this topic. Good luck with it. If you've got questions, come talk with me.